everyone. I'm going to tell you about this project on privacy-preserving smart contracts. This is joint work with my colleagues Ahmed and Zikai at Maryland and at Cornell, and with our advisors Elaine and Babis. It's been another interesting year for the cryptocurrency and blockchain world. Again, actually continuing many of the trends that we've seen before. So more investment in Bitcoin and blockchain companies. Another year, there's another potential explanation for who the inventor of Bitcoin is. Still no certainty this year. One of the things that's been a bit of a change of a trend is moving towards an understanding of a more generalized notion of what these kinds of systems give us. So if you've heard about Bitcoin in Oakland's past, you would have heard it explained as a payment system. So it's like a peer-to-peer network that implements a sort of virtual bank that keeps track of account balances for users. But really this underlying peer-to-peer network you can think of as providing a sort of more general interface. So instead of simply providing a virtual bank, what it's actually providing is a virtual general purpose trusted computer that can run arbitrary user-defined programs. And so these programs can still interact with money and allow users to exchange money with each other, but they can also have application-defined data and program behavior. The critical abstraction here is you should think of then the blockchain, this year's definition of the blockchain as a virtual trusted third party. A critical detail here is that it's trusted for correctness. It's going to run these programs correctly. And for availability, you can rely on being able to send data to one of these programs and have it be processed. But you can't rely on it inherently for privacy because this is a peer-to-peer network and everything that you send to this is public. The name for a program running on one of these systems is simply called a smart contract. It's not a legal contract, so don't be confused by that. This is just the name for a program running on one of these systems. So this has been really popularized recently by the recent success of one of Bitcoin's competitors called Ethereum, which launched its version 1.0 a few months ago. It's been in beta for about a year. As of just today, this has processed almost 5 million transactions so far. There are over 25,000 instances of these user-defined programs running on this public blockchain. And for comparison, this market cap is $1 billion compared to Bitcoin's $6 billion. This is now the second largest cryptocurrency, and it's sort of gaining on Bitcoin's heels. One of the nice things about this system is that it presents this attractive interface to program developers. It says, come use this programming language that we provide. You'll be able to implement all sorts of general applications, not just involving money, but things like auctions and crowdfunding campaigns, and even things like a kind of corporate governance structure where you can vote on proposals. And so if you follow one of their tutorials, you'll be walked through how to use their programming language in order to implement an auction. Now, there's a critical problem here, again, returning to this idea that this blockchain abstraction doesn't provide any inherent privacy. Well, a lot of the applications that you would care about implementing on this do require privacy. So all of the information that you send to the Ethereum blockchain is public. So the code of the programs that you're running is public. Any of the data you send back and forth is public. And the flow of money, critical monetary value is public as well. For some applications, this doesn't matter, but for a lot of the interesting applications, especially the ones with a financial nature, this is a big deal. So you would be revealing which kind of investments you're making, which kind of risks you're concerned about. This is all potentially business-critical information. Even more significantly, because in this peer-to-peer network, when you try to send a message to one of these programs, people on the network can see the message that you're sending even before it's committed. So if you try to implement something like a double price auction or some kind of stock market application, then an attacker would even be able to insert his own transactions and affect the output after seeing what yours would have been before yours get processed, so he can front-run orders. Let me give the concrete example then of what would happen if you try to implement naively following the sort of a tutorial guide of a sealed bid auction, like a second price auction in Ethereum. So it's very simple in the programming language to write the code for this auction. It would simply take in bids from all of the participants in the auction, and then after all the bids are collected, after some time limit, it would then process the output and dispense the right price. So in a first phase, users would make their bids, and in the second phase, the code would run and assign outputs. The problem is that from the very beginning, as soon as the first user makes a bid, this information is immediately available to the adversary. And in particular, this would allow the adversary to front run and violate the intent of the second price auction. The solution that we're going to propose for this is Hawk, which is a framework for privacy-preserving smart contracts. And the main idea that we're going to use here is zero-knowledge proofs. So we're going to have a protocol in which we're proving statements about commitments and ciphertext without revealing any of the underlying data. We're going to be using the same kind of suite of tools as some of the other projects we've heard about, like Cinderella. In a sense, this is also continuing a trend. So again, in some prior Oaklands, you would have seen the Zero Cash paper, which acknowledges that Bitcoin doesn't actually provide any transaction privacy. And so here, Zero Cash is an improved protocol that uses zero-knowledge proofs in order to provide this privacy. What's new in this year and recently is the idea of having more expressive, more programmable forms of cryptocurrencies like Ethereum. And so we're, with Hawk, trying to do the same thing, making privacy-preserving, adding the privacy-preserving quality back in, but still preserving the expressive programmability that's desired. So let me walk through at a high level how the Hawk protocol would work for this auction example. So first of all, this is going to be built on top of the Zero Cash protocol, so we use this as a kind of the underlying substrate. It's going to be our building block. Instead of simply having the code for a contract, the direct code for it placed on the blockchain, what we would do is have the users generate zero-knowledge proof parameters, so they will actually take an encoding of the function that they're going to run, and the first step will be to generate a zero-knowledge proof public parameters, and that's going to be stored on the blockchain. The users are going to go through several phases, and so in the first phase, all of the users are going to send their bids to the blockchain, but instead of sending them in plain text, as in the previous example, they're actually going to send a commitment to the bid that they are placing, along with a zero-knowledge proof that attests to the fact that they actually have the authority to spend this money, that it hasn't already been spent before, and that this amount actually exists. After this first phase, after all of the commitments to the bids are placed, then in a second phase, the users are going to reveal what their bids were to a minimally trusted party called the manager. And I'm going to talk more about the manager in just a moment. So what the users do is actually send an encryption to the manager's public key of what their bids were, of what the opening of these commitments were. And they send these directly to the blockchain as well. After the manager has seen and decrypted all of the users' bids and inputs, then he's able to run the function himself. And he's going to create encryptions of the outputs to each of the parties according to the program's policy, along with a final zero-knowledge proof that attests that he ran the intended application function correctly, and that he included all of the user's input, and that all of the inputs that he provided on behalf of the users were consistent with the user's commitments. Now, you should be totally skeptical at this point because I've introduced this apparent trusted third party, the manager. So what I want to do is describe exactly what the trust model is here and what the manager can get away with. We don't need to trust the manager for correctness because the manager is going to provide a zero-knowledge proof that the function he evaluated was run correctly. We don't need to trust the manager for input independence. And what I mean by this is in the auction scenario, because the manager doesn't see what any of the user's bids were before all of the commitments to the bids are placed, even the manager doesn't have any opportunity to front-run bids in this auction. As I mentioned, this is built on top of the Zero Cash protocol. And so what happens is that even if the manager goes bad in some way, nothing that the manager can do can affect either the security or the privacy of the underlying eCash that this is built on top of. We also don't have to trust the manager for fairness because if the manager goes away and, say, fails to complete the last step of this protocol, the fact that he failed to do this would be publicly visible, and so we require all of the parties to place collateral deposits which would then be paid out to the other users as compensation in the case that someone aborts in the protocol or the manager fails to complete this last step. The only thing that we do have to trust the manager for is posterior privacy, because the manager does see by the end of the protocol what all of the users' actual plain text inputs were, and so he could leak those if the manager goes bad. And I should mention that if we have multiple instances of these contracts, so like different instances of auctions or different instances of other applications, you can have different managers for each instance, and so if a manager in one goes bad, it doesn't automatically leak any of the details of the other instances. You should think of this manager also as a logical role, so you could imagine implementing it with multi-party computation or even in trusted hardware to get some extra guarantees that this posterior information wouldn't leak out. Looking ahead, the performance metrics that I'll show you reflect just the simple case where the manager runs just as one party. Now, we could have just implemented the auction protocol and addressed that, but again, the goal here is to be able to have a user or application developer-friendly programming framework capturing kind of the ethos of Ethereum. So our goal is instead going to be provide a compiler that application developers can use without having to think about the underlying cryptography, but they can use this to specify the application that they want, and it's going to be the job of our compiler to generate a correct by construction cryptographic protocol that implements what they want. The way that users provide input to the hot compiler is by writing their application in a basically just in C with very minor modifications that provide some keywords and data structures to talk about the input monetary values as well as arbitrary input values for the parties. But otherwise, this is simply, they just define any computable function in C, so they provide this one function, and then that's going to be the specification for the application. And in our paper, you can see what the example looks like in the actual code, because you can write these applications in very short, concise code that's easy to read. So we provide examples for the auction scenario, but also for a two-party gambling game, as well as a crowdfunding campaign where you get the money back. Everyone who donates gets the money back if it doesn't reach some threshold, as well as a really simplified financial instrument that allows you to bet on the price of a stock, as reported by some stock price authority. Just to give a really simple overview of what the steps are of our compiler, because we use a bunch of separate tools. The first step is that we actually use the existing Pinocchio compiler from several Oaklands ago. This compiles the user's program from C into an arithmetic circuit, where again the arithmetic circuit is sort of the native language for the zero-knowledge proof framework we're going to be using. The user's code, when it's compiled to this arithmetic circuit, gives you a fairly simple circuit because it doesn't have much cryptography. But our protocol is about making zero-knowledge proofs about the contents of encryptions and commitments. And so what we have to do is basically build a circuit around the user's application subcircuit. And this circuit, this augmented circuit, has to contain statements about cryptography. And so what turns out is that this requires a lot of care in order to implement in an efficient way. So most crypto schemes are designed to be efficient when implemented on general purpose hardware like 32 or 64-bit computations, and in this arithmetic circuit world, we have to make different protocol choices. And so in the paper, you can see more information about the choices that we use. In particular, for encryption, we use a hand-optimized implementation of RSA that fits neatly into this arithmetic circuit. And this insight, I think, is similar to the one in Cinderella, which also had a similar problem and addressed it in a similar way. This augmented circuit we develop with our own arithmetic circuit compositing library called JSNARK, which is open code that's available online. The last step after building this augmented arithmetic circuit is to simply provide this arithmetic circuit to an existing zero-knowledge proof library, libsnark. So again, the same tool set as the other talks that have used this suite of tools. Just to give some examples of then our performance, so we implemented this and tried it out on several scenarios. So in particular, I'll give you the example for a 100-user auction or crowdfunding campaign. This is all also at the 112-bit security level. The auctioneer, the manager's part, is the most computationally expensive, and this takes about nearly 3 minutes to run. This is actually parallelized across 4 cores on an Amazon machine. The amount of computation needed for the users to do is much smaller. It's only 40 seconds, and this is only on a single core machine. The manager's effort scales linearly with the amount of users who are participating, because that corresponds to then the size of the final circuit he has to create a proof about, whereas the user's computation is independent of the number of users. The main overhead here is computing the zero-knowledge proofs. There is other cryptography, but the cost of that cryptography is minimal in comparison to computing these proofs. Probably the most critical cost metric, though, is what's the cost to the blockchain itself. So what's the size of the transactions and amount of computation that everyone on one of these blockchain peer-to-peer networks needs to run. And again, on the blockchain, the only thing that's happening is that the peer-to-peer network is verifying the proofs, not computing them. So in this example, the cost of verifying all of the proofs needed for this auction example is a total of 1.5 seconds, which we think is acceptable. The total amount of transaction data, the total amount of data of all of the proofs together that you need to place on the blockchain is 220 kilobytes. Just to give you then a quick explanation of some of the other things that you'll find if you look at our paper. So we provided a formalization and proofs and protocol specification in our paper. These is in the universal composability model. This requires us to provide a UC model of what existing blockchain systems give you, and then also a UC formalization of what our specification is that outlines exactly what the failure modes are and everything that's captured by the specification. In particular, this UC blockchain framework would be a good starting point for someone to be able to use as a starting point for modeling other applications you might want to build on top of a blockchain. In order to make this proof go through in the UC environment, we had to come up with a construction that allows us to leverage the underlying lib-snark scheme, which is not itself UC secure, but we're able to add a transformation to it that makes it UC secure. And then the software that we have available already online, you can see our JSNARK circuit compositing library. The code for the Hawk project itself is going to be online soon. We're getting around to that. Okay, so I'm going to finish there. There's our paper link, and we'd encourage you to try out our JSNARK software in particular now and to look forward to the Hawk code when it's released. All right, thank you.
Very good talk, thank you.
Thank you.
So you talk about two main issues such as privacy and programmability. But one other issue that people talk about is sufficient decentralization. In other words, how do you prevent or ensure that malicious collusion isn't happening? So is this something that you have looked at or the community is actively looking at?
I would say the community is actively looking at this. Do you have a more specific sense of what kind of collusion do you mean?
Well, people have found that in certain scenarios, when miners reach a certain fraction, when collusion reaches a certain fraction.
Sure, absolutely. So this work entirely builds on a sort of abstracted model of what blockchains give you. So we essentially assume that they work as a black box. We don't, in this project, don't say, we have to assume that the underlying blockchain, what it gives us, it does so securely. So this includes not having all the transactions reverted or taken over, which are realistic attacks to worry about in these systems. But for our purpose, we use that as a black box.
Okay, got it. Thank you.